Okay, definitely.
We'll be getting started soon. We'll just wait for some more people to join, then we'll start.
No, June and only we're taking, but July while they
Okay, guys, we'll be waiting a couple more minutes for more people to join. Get started at like 10:32 to let the last couple people roll in. Okay, guys, I guess we'll get started. Thank you for joining me and Adam today. So, welcome to Intro to Physics. I'm Andrew, and I'll be teaching this course alongside Adam. So, you guys have signed up for a 2-week long introductory physics course where we'll be teaching you guys like the foundations of physics and prepare you guys for any future physics classes you guys may take in middle or high school. So, we have some quick reminders before starting. So, the first one, like I said in the email, is make sure to use the chat with respect. Right now, we have it as you can only talk to host and co-host for now, but depending on the lesson, we may open that up to everybody. So when we do that, please do not abuse the chat. Secondly, make sure that you're muted throughout the meeting unless we call on you after you raise your hand. Third one is just have something to write stuff down with. It doesn't matter if it's like a physical notebook or digital notes. We just recommend that you have something to write down with so you have notes and you can use them when solving problems. Fourth, you can raise your virtual hand to ask questions, or you can ask to the chat where either Adam or I will be answering depending on the day. So today I'll be lecturing, so Adam will be in chat answering questions, and tomorrow Adam will be lecturing, and I'll be in chat basically answering any questions. So let's say we have a question come up there, and I give you guys like a minute to solve a question, right? When it's time to relay answers, you can either send your answer to the chat to us, or you can raise your virtual hand, and I'll call on you and you can explain your answer. And today's class may end a little early or late depending on the timing because it's the first day and we're trying to basically sort things out. So here's a quick about me. I'm Andrew. I'm a rising senior at Cupertino High School. And one fun fact about me is I've played soccer for 12 years, and Adam and I play on the soccer team right now together.
Okay, hello guys. I'm Adam, and I'll be your other teacher for this week. I'm also from Cupertino High School, and one fun fact about me is that I like taking naps.
Okay. So here's our kind of 2-week plan of how we're gonna basically teach this course. So today we'll just have an intro to physics, like what is physics? We'll talk about units, measurements, and vectors, because physics is the study of how the universe works by understanding motion, forces, and energy, right? So we'll introduce basic units of measurement and the difference between scalars and vectors. Tomorrow, Adam will go about motion in one dimension, so 1D kinematics along with graphs. So you'll learn how objects move in straight lines and like how to describe that motion using like position, velocity, and acceleration, and how graphs can help you visualize those changes over time. Wednesday will be vectors and motion in 2D kinematics. So we'll expand motion into 2 directions at once, like when an object is moving along like a curved path, and you'll learn how to work with vectors to describe movement in 2 dimensions. Thursday will be our first lesson on Newton's first law, and you'll explore what forces are and how they cause objects to stop, start, or keep moving. So we'll explain that objects stay in rest or in constant motion unless acted on by an outside force. And our last lecture date this week will be Friday on Newton's second law. So we'll show how force, mass, and acceleration are related using F equals ma. And we'll just explain how applying more force or having less mass changes how quickly an object kind of speeds up. So after that, we'll have the weekend, and we'll come back to the second week. And on Monday, we'll go over Newton's third law, which is, again, more on force, mass, and acceleration. And you'll learn that every action has an equal and opposite reaction, meaning forces kind of come in pairs. Tuesday will be applications of Newton's laws plus friction. So we'll apply Newton's laws to actual real life situations and include how friction opposes motion and affects how objects slide or roll. Wednesday, we'll move on to circular motion, orbits, and gravity, and you'll explore how objects move in circles, what keeps planets orbiting the sun, and how gravity kind of pulls objects toward each other. Thursday will be our final lecture day, which we go on momentum, energy, and work. So we'll explain how moving objects can carry momentum and energy and how work is done when a force moves an object over a distance. Friday will just be kind of a final review day, so a day to go over everything we learned so far, maybe clarify any doubts you guys had over the last 2 weeks, and we'll probably host like a large Kahoot for the majority of that class. Do you have any questions so far? All right, I guess I'll move on then. So here's today's agenda. So we did our introduction already. Then we'll have some concept introduction, some practice questions, and then we'll end with closing. So what is physics, right? So physics is the study of how the universe works. It helps us understand the rules that everything in the world and even the entire universe follows. From the tiniest particles to huge galaxies, physics explain how things move, change, and interact with one another. So in physics, we used applied math and experiments to figure out the reasons behind these changes and movements. So for example, physics allows us to predict how high a ball will fly when you throw it, or how fast a car will reach its destination. So it helps us understand forces like gravity that pulls objects towards the Earth, energy that powers everything from, let's say, a flashlight to a rocket, and motion that makes everyday activities possible. So whether it's the light we see, the sound we hear, or the electricity that powers our devices, physics reveals like the why and how behind all these natural phenomena. So by learning physics, we gain a deeper appreciation of the world around us, and we can develop tools to invent new technologies and solve important problems in our society. So one important thing that you guys need to know for any future science classes or as jobs with engineering are SI units, right? So SI units or International System of Units are kind of like the standard way scientists and engineers measure things like length, mass, time, and temperature. So using SI units is very important because it makes communication clear and consistent all over the world. So for example, instead of saying something is about a foot long, scientists would use meters so everybody knows exactly what that means, right? So the system helps avoid confusion and makes it easier to like kind of share results, compare data, and like work together on experiments or projects, like no matter where you are on Earth, right? So there's no confusion at all. So here are some examples of SI units, right? On the left side, you'll see length, mass, and time, which we'll be covering a lot today and the next couple of days. And there's this meters, kilograms, and seconds. And it's important to carry the units on when you have the answers, right? So you know, like the people checking your work can see what you're actually working on. And we also have force, pressure, energy, and power, which we'll be covering kind of later on in our lectures. And you will see that SI prefixes on the right side, right? So sometimes the numbers we're measuring are either like really big or really small, right? And writing out all those zeros would kind of be a pain, right? So that's where we use SI prefixes. So they're kind of short words or letters added to units to show like multiples or fractions of a base, right? So they help us scale measurements without changing what we're actually measuring. So let's do some unit conversion practice questions. So the first one is convert 5,000 millimeters to meters. So your choices are 0.5 meters, 5 meters, 50 meters, and 500 meters. I'll give you guys around 30 to 40 seconds to solve it, and you can put your answer in the chat or raise your virtual hand. All right. Sanjita, I think you raised your hand first. What did you think?
5 meters.
Yeah, you're correct. Yeah, because we find out that 1,000 millimeters are on the right side you see is 1 meters, and if you multiply both sides by 5, you get 5 meters. Okay, let's do the second one. So convert 3.2 kilometers to meters. Your answer choices are 32 meters, 320 meters, 3,200 meters, and 32,000 meters. I'll give you guys another like 30-ish seconds. Yeah, I think Sujan, I saw your hand up. What did you think?
3,200 meters.
Yeah, you're correct, right? Because we can see that 1 kilometer is 1,000 meters, right? So we multiply by 3.2 and we get 3,200 meters. All right, let's do some more unit conversion. So number 3, convert 250 centimeters to meters. And also thank you to those who are also putting in the chat. I see your answers as well. Yeah, Reedy, you can go.
Yeah, so the answer is 2.50 meters.
Yeah, you're correct, right? Because 100 centimeters is 1 meter, right? And then we can multiply by 2.5 and we get 2.5. Okay. Yeah, all right, let's move on to the next one. Number 4, convert 1.5 kilograms to grams. Okay, Arjun, yeah, you can go.
1,500.
Yeah, 1,500 grams, yeah. Because obviously 1 kilogram is 1,000 grams. We just multiply by 1.5 and we get 1,500. Our last one is a block of wood has a mass of 2,000 grams. What is this in kilograms? Yeah, Jaden, you can go.
2 kilograms.
Yeah. Yeah, it's important to include your units, right? So it's 2 kilograms because 1,000 grams is 1 kilogram. We multiply by 2. All right, good job, guys. On. So we'll do one last unit conversion. This will be a little bit different. So if a car travels 36 kilometers in 1 hour, how many meters per second would that be? I'll give you guys like a minute for this one. And on the next slide, I'll show some work for this question of how I would solve this question. Oh yeah, also if I already called on you and you have your hand up, can you please lower it, please? So I don't call anybody new. Yeah. Okay, does anybody want to share their answers? Yes, Sanjita, you can go.
I think it's 10 meters.
Yeah, 10 meters per second. Yeah, I'll show my work right here. All right, so we have 36 kilometers, right, in 1 hour. It's 36 kilometers in 1 hour, right? So we can do what we call dimensional analysis. So we can just basically say 1 hour, right? 1 hour is what in seconds? That'll be 3,600, right? And let's do it for kilometers. 1 kilometer is 1,000 meters, right? So you can basically cancel these out, right? Kilometers, hours cancels. and then we can just multiply the top and bottom, right? So you get 36,000 at the top, and we get 3,600 at the bottom, right? And we have meters and seconds still here, right? Because these are left, right? Meters, seconds. So we can, yeah, we get 10 meters over seconds. Good job, guys. All right, let's move on to the next part. So next are scalar and vector quantities. So scalars and vectors are two types of quantities we use in physics to describe things. A scalar is a quantity that only has a size or amount, right? Like temperature, distance, or time. So it doesn't have a direction, just a number. So for example, you can say it's like 25 degrees outside, and that's a scalar because it tells you how hot it is, but like not in which way, right? A vector, on the other hand, they have both size and direction. So examples include displacement, velocity, and force. So if you say a car is moving 60 miles per hour north, that's a vector because it tells you how fast the car is going and in which way, right? So understanding the differences helps us describe and predict how objects will move and interact in our world. Next is distance versus displacement. So distance is the total length of the path that an object travels, so no matter which direction it goes. So it tells us how far something has moved, but it doesn't really care about the direction, just the amount of ground covered. Because distance measures how much ground is covered, it can never be negative. So distance is a scalar quantity because it only has size, but no direction. So for example, if you walk around the block and end up where you started, your distance traveled is the total length you walked, even though you didn't end up in a new place. Displacement, on the other hand, is a change in position of an object from where it started to where it ended. So unlike distance, displacement considers direction. So it can be positive, negative, or actually even zero, depending on which way the object has moved. So displacement is a vector quantity because it has both size and direction. For example, if you started at home, you walk 5 meters east, then 5 meters back west to where you began, your displacement is zero because you ended up in the same place, even though you walked a total distance. So we'll have an example here, right? Let's say you're at position 0 right now on the line graph on a bicycle. Let's say you biked 5 units to your right. So your total distance traveled is just 5 units, right? And your displacement is also 5 units because that's your change from your starting position. But if we see here, let's say you biked 5 units to the right and then you biked 2 units back. So your total distance traveled would be obviously 7 units because you go 5 back 2, that's 5 plus 2 is 7. But your displacement here would only be 3 units because that's your change in your position from your initial spot. Okay, let's do some practice questions on these. So number 1, a student walks 3 meters north, then 4 meters south. What is its displacement and displacement? Distance and displacement. I'll give you guys like 30 seconds for this one. It's pretty quick. All right, Sujan, you can go.
-1 units.
So distance ಅಂತವಾಗ ಹಚ್ಚಿಸೋದು
Can you repeat what you put for
-1
distance and
units. -1.
ಅದೇ units
could you repeat what you said for distance, please, again? We couldn't hear distance.
Oh, distance is a 7, and then displacement is a 1. No.
Yeah.
Yeah.
Yeah, so our distance will, yeah, correct. It would be 7, and yeah, displacement would be -1 if we put north as positive. So you can also say 1 meter south. So it's important to kind of establish your coordinate system. Like if you say north is positive, then yeah, it would be -1. All right, let's do the second question. So a girl runs 100 meters around the track and ends up where she started. So what's her distance and displacement? Yeah, Aryahi, you can go.
The distance is the 100 meters that she ran, and the displacement would be 0 meters.
Yeah, you're correct. Yeah, because obviously she travels 100 meters on the track, but she ends up where she started, so it would be 0 meters as her displacement. Alright, let's do 2 more. So number 3, a delivery drone flies 12 blocks east, then 5 blocks west. What's the total displacement and distance for the drone? Yeah, Rihan, you can answer this one.
So the total distance is 17 and displacement is 7.
Yeah. So total distance, yeah, would be 17. And your displacement would be 7 blocks east. So make sure to include that unit at the end. But yeah, good job. All right, we'll do this last question. We'll do it's a little bit of a challenge, but Andrew walks 3 meters north, then 4 meters east. What's the distance traveled and what's his displacement from your starting point? So one hint is to use the Pythagorean theorem for one part of this question. And I'll also go over a diagram for this one as well. Wait another couple more seconds. All right, Rihan, you can go again.
And the total distance is going to be 7 and by the Pythagorean theorem it's 5.
Yeah, because let me just draw a diagram for this one. So let's say let's draw a coordinate plane, right? Say these are your 4 quadrants. So let's say I'm at the origin here. I'll travel 3 meters to the north, and then I'll do 4 meters east, right? So obviously I'll be at this position. So obviously distance traveled is 3, 4, so it'd be 7, right? But your displacement will be obviously using Pythagorean theorem. So since this is a 90-degree angle, and this is a common sort of like 3, 4, 5 triangle that you see for Pythagorean theorem. So it's 3, 4, 5. So the hypotenuse is 5, and that would be your displacement. All right. Any questions so far or anything that we covered?
What's a hypotenuse?
Oh yeah, hypotenuse. So in a 90-degree triangle, you'll have kind of 2 parts. Let me show you here. So we have a triangle here, right? So we'll label this side A, B, and C, right? So this hypotenuse is the longest side of the triangle, and you can find it using a squared plus b squared equals c squared. So if you know 2 values of the Pythagorean of the triangle, you can use the Pythagorean theorem to solve it. So in our case, A was 3 and B was 4. So we can plug in, right? So it'd be 3 squared plus 4 squared equals c squared. So this would be 9 plus 16, right? So 25 equals c squared. So we can root both sides and get c equals 5 for our hypotenuse, which is the longest side of the triangle, basically.
Oh, okay, I get it.
All right, let's move on to the next part. Wait, does anybody have any more questions or is that fine? All right, I'll move on then. So motion, right? So motion is the change in an object's position over time. So it means something is moving from one place to another, and we can observe this by comparing where the object starts and where it ends up. So understanding motion can help us explain why, how, and why things move, right? Which is important from everything from sports to science and technology. So motion isn't just about things you can see, like moving fast, like cars or runners. It's like also happening when leaves fall gently from trees, or actually when planets orbit the sun far away in space. So by studying motion, scientists can predict where objects will go, how fast they'll move, and what forces are kind of acting on them. So whether it's a ball being thrown or a bike speeding down a hill, motion is just happening around us all the time, right? So the first part of motion is speed, right? So speed tells us how fast something is moving. So it measures the distance of an object travels in a certain amount of time, like miles per hour or meters per second. So speed doesn't tell us the direction, just how quickly the object is moving. So it's a scalar quantity. So for example, if a car is driving at 60 miles per hour, that means it covers 60 miles every hour. So no matter which way it's going. And speed can also change as well. So you can start running slowly and then sprint faster. That's a change in speed, right? So understanding speed can help us know like how long it will take to get somewhere or how fast an object is moving in sports, cars, or even animals. So it's an important part of studying motion because it tells us the rate at which the position changes over time. So the formula for speed is obviously distance over time, and the SI unit for speed is meters per second. Let's do some practice questions with speed. So the first one is if a car travels 400 meters in 20 seconds, how fast is it going? I'll give you guys like 20 seconds for this. Yeah, here you can go.
It goes 20 meters per second.
Yeah, nice, because its speed is distance divided by time, so it's 400 meters divided by 20 seconds, so it'd be 20 meters per second. All right, number two, how much time will it take for a bug to travel 5 meters across the floor if it's traveling at 1 meters per second? Yeah, Arjun, you got it.
It'll take 5 seconds.
Yeah, you're correct. Yeah, because time is distance divided by speed. So 5 meters over 1 meters is 5 seconds. All right. Last one is how far can you get away from your little brother with the squirt gun filled with paint if you travel at 3 meters per second and you have around like 15 seconds before he shoots you? Alright, yeah, Sanjita, you can explain your answer.
I think it's 45 meters in 15 seconds because if she can, or if they can travel 3 meters per second, you just have to multiply 15 by 3.
Yeah, you're correct. Exactly how I would explain it, right? So distance is speed times time, so it'd be 3 meters per second times 15, you get 45 meters. Alright. Next is velocity, right? Velocity is like speed, right? But it also includes direction, like the direction something is moving in. So it tells us how fast an object is going and which way it's also moving. So for example, if a car is driving, let's say north at 50 miles per hour, that's its velocity because it shows both speed and direction. So velocity is a vector quantity, so it has both size and direction. If a car turns around and goes south at the same speed, its velocity changes because the direction has changed, even though the speed remained the same. So knowing velocity can help us understand more about motion and how objects move in real life, because it's far more realistic that like objects will not move in a straight line, right? It's gonna twist and turn around, right? So it's far more realistic. So velocity is obviously displacement over time, and how you can notice that displacement is also a vector quantity, right? And how speed is distance is a scalar quantity. So and the SI unit for velocity is the same as speed, right? But we just have to take into account the direction also. Okay, let's do some practice questions on velocity. So the first one is a car moved 80 kilometers to the south. What is its displacement?
I have a question.
Mhm.
Would north be like the positive factor and like south negative, or?
Yeah, that's like how it's like commonly like used, right? Because north is seen as up, right? So it's commonly seen as positive and south as negative. But in physics, you can kind of set your coordinate systems like how you want. Even if you predetermine that, even if if you say south is your positive, then you can put that as your answer. But most commonly use north for positive and south for negative, right? But it's up to you to kind of establish your coordinate systems for physics.
All right, sure.
Yeah, Vishnu, you can answer this. Wait, Vishnu, I don't think you unmuted.
Oh, I think it's negative 80.
Yeah, it'd be the displacement would be 80 kilometers. It would be 80 kilometers to the south, right? So because, and you can say negative 80 if you set the coordinate system, right? Obviously, it's more common that south is negative, so yeah, negative 80. Let's do number 2. So Adam ran 400 meters north in 60 seconds. What is his velocity? So also make sure to include your kind of direction too in your final answer.
Is it supposed to be 400 like in seconds or per second or per minute?
Answer, you can convert it any way you want, but we would prefer it like meters over seconds, right?
Okay.
Because in the question, if it gives you the units as meters and seconds, and it doesn't like explicitly say to convert it to like, let's say kilometers per minute, like you don't need to do that. Just use the units that they give you in the question and use that in your final answer.
Okay.
Yeah, alright, you can go.
Is it 6 2/3?
Yeah, you're correct. Yeah, 6.67 meters second, but it's obviously to the north, right? So just make sure to include that it's going north. But yeah, otherwise you're correct. All right, the last one is Andrew took 90 minutes to bike to his grandmother's house, which is a total of 6 kilometers. What was his velocity? Remember, guys, are finding the velocity.
Um,
Wait, do we do velocity in like seconds or minute?
You can put it in any units, but I would prefer you do it in minutes, but you can also do hours as well for this question. Does anybody have an answer? Oh, yeah, Vishnu, you can answer.
Oh no, I left my hand up. I didn't.
Oh, yeah, good. Yeah, Jane, you can talk.
15 minutes per kilometer.
Yeah, that's correct, right? You can, obviously, that's the way I would answer this question as well, but you could also probably convert 90 minutes to seconds or hours, right? So 90 minutes to an hour and a half. So that'd be 6 kilometers by 1.5 hours. So 4 kilometers per hour would also work, but you can convert it any way you want, basically. All right. Let's go over a quick summary of what we did today. So first, we talked about SI units, right, or the International System of Units, and how they're kind of like the standard measurements scientists use all over the world. So they help everybody speak like the same measurement language, so there's no confusion about how long, heavy, or hot something is made. So, for example, length is measured in meters, time is measured in seconds, and mass in kilograms. So using SI units makes sharing and comparing these scientific results easier and far more accurate. Next, we talked about scalar versus vector quantities, right? So scalars are quantities that only have size or amount, like temperature, distance, or time. So they don't include any direction. So for example, if it's 30 degrees outside, that's a scalar because it tells you how hot it is, but not in which way. So vectors, on the other hand, they have both size and direction. So examples include like displacement, velocity, and force. So saying a car is moving at 60 miles per hour in an artificial vector because it tells you how fast and in which way it's moving. Next, we talked about this distance versus displacement. So distance is the total length of a path an object travels. So no matter which way it goes. So it can never be negative, and it only tells you how much ground was covered. But displacement is different, right? Because it measures a change in position from the starting point to the ending point. So including direction. So this means displacement can be positive, negative, or zero. Like we learned in the practice questions, like when a student goes down the track, your displacement would be 0. So if you walk 5 meters east and then 5 meters west, your distance is 10 meters, but your displacement will be 0 because you ended up back where you started. And the last thing we covered was speed versus velocity. So speed told us how fast something was moving and calculated it by dividing the distance traveled by the time it took. So it doesn't include direction, so it's just scalar, right? The velocity, it includes both speed and direction, making it a vector. So the car's traveling at 15 miles per hour, that's its speed. But if it's driving at 15 miles per hour east, that's its velocity because it includes the direction. So velocity can either change either the speed or direction changes. Alright, before we leave, let's do one last question, kind of tying up everything that we learned today. So say Adam walks 6
Wait,
meters
Andrew,
forward.
I think your voice is like a little laggy. Can you like maybe check your Wi-Fi?
Wait, I'll just repeat the last summary slide then. Wait, when was it choppy?
Choppy since like the first summary slide.
Alright, I'll just repeat that then.
I think I can cover for you if you want. I can cover it for you if you want. But
Is it still laggy?
yeah, it's laggy right now.
Alright then, yeah, you can take over if I'm still lagging. Yeah.
All right. Okay, so summary of what you guys did today. So SI units, basically standard units that you guys are going to use in the physics classroom. Mostly going to see meters, seconds, things like that. You also have to a lot of physics problems will throw a lot of random units at you, and you're gonna have to convert it back to common units like meters per second or things like that. So a question might give you like, let's say kilometers in hours, and then the problem will want you convert that unit back to meters per second. So you guys will know you guys need to know how to do that. And then scalar versus vector quantities. Remember, scalar quantities only have a magnitude. They do not have a direction. They only have a value of how big they are, okay? Vectors have a magnitude and a direction. They have a magnitude and a direction. Let's say things like velocity, acceleration, things like that. So if you have a question asking you to answer in if you have a question asking you to answer a vector answer, then you have to include a direction also alongside with your magnitude, okay? Okay, distance versus displacement. Remember that distance is how far you have traveled on your path, okay? The total distance of your path, okay? Displacement is your change in position, okay? So remember, if you walk forward 5 meters, but then you walk back another 2, your displacement is going to be 3 because that's how much you changed your position, right? Only 3 meters. Although your total distance traveled would be 7 meters, right? Because you traveled 5 meters forward and then another 2 meters backwards. So that would be 7 meters in distance and 3 meters in displacement, okay? And speed versus velocity. Speed is how fast you can go. Remember, it is the formula for this is speed equals distance over time, and it is a scalar quantity, so you do not have to include a direction with this. But a velocity is speed, basically speed with direction. And the formula for this is actually displacement over time. Please remember this. It is not distance over time. It is displacement over time. So let's take the previous example, right? Let's say you go 5 meters forward and another 2 meters back. Okay, your total displacement is 3 meters, right? Let's say you covered that distance in let's say 3 seconds, right? So your velocity would actually be 3 meters over 3 seconds, right? Because that's displacement over time. So your displacement is 3 meters and your time is 3 seconds. So your velocity would be 1 meter per second. But if I asked you how much your speed would be in that situation, 5 meters forward and another 2 meters backward, your total distance would actually be 7 meters, right? So you would plug in 7 meters on the top, and I gave you time, and your time was 3 seconds. So it would be 7 meters, 7 over 3 meters per second. Okay, please remember that. I think. Wait, Andrew, can you give me co-host on my other account? I think it's just lowercase Adam in the Zoom meeting. And then I can like share on my iPad.
It's just lowercase, I guess.
Yeah, lowercase Adam. Oh wait, I don't think I could find the slides, so hold on. Give me a sec.
I can explain. I'll explain this. It's just still laggy.
Yeah, it's still laggy though, but if you're hold on. Wait. Let me try sharing on my iPad then. Okay. Why is it do I'm still on Zoom? It's my bad. Keynote. Let's go to the problem then. Okay. Final question. Okay. Adam walks 6 meters forward, then turns around and walks 2 meters back with a constant velocity the whole time. The whole walk takes 20 seconds. Okay. What is the total distance traveled? What is the displacement from the starting point? What is Adam's speed? And what is Adam's velocity? Include directions. So yeah, let's just do the first problem on this slide here then. What is the total distance traveled? Okay. I walked, let's say my starting point is here. I walk 6 meters forward. Okay, that's 6 meters. And then I walk 2 meters back. Okay, that's another 2 meters. So I will just add those two together, right? 6 plus 2 equals 8. Okay. So that would be 8 meters, right? 8 meters traveled. What is the displacement from the starting point? I walked 6 meters forward, then I walked 2 meters back. That would be 4 meters, right? I would be 4 meters away from my starting point. So that would be 4 meters. What is my speed? Okay, remember the formula for speed? Speed equals distance over time. So I'll just plug that in, right? What is my total distance? 8 meters, right? 8 meters. And the whole walk takes 20 seconds. So that would be 20 seconds at the bottom. So it would be 2/5, right? 2/5 meters per second. So that would be my speed. Let's try moving on. Actually, it's kind of weird. Oh, okay. If you don't mind doing on the same slide then. Okay. What is my velocity? Remember, velocity equals displacement over time. Okay, what is my displacement? 4 meters. Solved that already. And what is my time? Still 20 seconds. So that would be 1/5 meters per second. And what is directions? Remember, this is velocity, so we have to include directions. In this case, we're walking forward and backwards, right? So I think we just put forward, then back. Okay, so if a teacher gives you like a question like this, I think it's safe just to put both directions. Forward, then back, just to be clear. I think that's it for today. Yeah, looks like we ended 5 minutes early today. We will take note of that. Do you have any questions? No questions. Okay. Well, then I think we'll end the class a little early today. And I think me and Andrew will see you guys tomorrow. Okay. Bye, guys.
Bye.
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 Bye, guys. Andrew, can you end the meeting, maybe?
Wait. All right, guys. Thank you for joining us today. Yeah, we'll see you guys tomorrow.
Bye.
Bye.
I'm gonna pause